Hi and welcome to this section where we are going to have a look at complex numbers. So I'll be sharing material in our resource book which I have shared with you. Okay. Yes. So okay. Close the page. Okay, so the content, we shall look at the introduction, a few properties, as outlined here in the content, in the outline here. So here we have the introduction. They give us a background of complex numbers when people are trying to solve cubic equations in the 16th century. Well, they don't want to go so much in detail in that, and so on. Still we have a history here, and then they give us scenarios where they can arise if we are trying to find the roots of quadratic equations, and we are faced with situation where we have the discriminant here is negative, the one under the root. Okay, if it is negative, so how would we deal with that? Trying to find the square root of a negative value here, and so on and so on. Okay, so we can jump into the properties here. Now the notation here is this. Okay, z equals to x plus jy, or some people decide to write it with iy. Whatever the case, j or I is the square root of -1. This is called the real part, okay, and y is its imaginary part. And we always abbreviate it that if we have this z as our complex number, x is the real part of z, and y is the imaginary part of z. Okay. So if we have a value as this, the real part is 3. And then the negative part is so the real part is 3, and then the imaginary part is -2. Okay, you don't have to mind about the j, just know that the j is simply giving it the j is simply telling us that the -2 is the imaginary part. So we can represent this on an angle diagram here geometrically. And it's the same, just like the way we have been plotting on the coordinate axis. So the vertical scale is for the imaginary, and then the horizontal scale here is where I represent the real part. Okay. For example, we have a few examples there in 3.1 in which we are going to represent those numbers on an angle diagram. So the first one is 3. So on the horizontal scale, you have the 3 here. Okay, you have the 3 on the horizontal, and then on the vertical you have +2. Okay, so if it is that, then you just look for the -5 and +3, and so on. If it is -2 minus j3, so we look for the -2 on the horizontal and -3 on the vertical. Okay, so that would be D. So we look at a few arithmetic here. Equality: if two complex numbers, that is z1 and z2, are equal, okay, then they are represented by the same point on the angle diagram. And clearly, if they are represented by the same point, it means that the x coordinates and or the real part, okay, is the same, and also the imaginary is the same for both numbers. So for example, if we have this z1 here and we have z2, if they are equal, then it's just a matter of equating the real part. Okay, 3a minus 2. Okay, the real part 3a minus 2 equated to the real part here, b plus 1, and same here, the imaginary part here 3b minus 1 to the imaginary part here. Don't forget the negatives. Okay, negative a plus 2 minus b. So that's all they do here. They equate, suppose this was the real and then this is the imaginary, and then you solve that simultaneously, or whichever way you want. Oh yeah, it's simultaneously, and then you get the solutions. Okay, addition and subtraction, it follows this very simple procedure. You just add the real part to the real part and the imaginary part to the imaginary part. The same is with subtraction. Subtract the imaginary part and then the real part separately. Okay, so you have a few examples there which you can simply understand. And then when multiplying two complex numbers, the same rules, normal rules for multiplying out brackets hold. Okay, for instance, if you have z1, if we have z1 as that and z2 as that, then if we are to multiply them out, z1 times z2 is simply that, and then you just open out the brackets. Okay, this multiplied with that, then this multiplied with that, and then this multiplied with that, and then this multiplied with that. Okay, that is all we do here. And then you make use of the fact that the j squared is -1, and then if j squared is -1, then we know this is going to be, so if j squared is -1, then we know this is minus y1 y2. Okay, so you have x1 x2 minus that, and then here you factor out the j, and it's just, anyway, it's just algebra here. That's all you do. And then you can follow through the example 3.4 in multiplying them. Okay, and yes, I think you can simply follow through. Division is less straightforward. If z1 is if this is our z1 and this is our z2, then we use the following technique to obtain the quotient. Okay, we multiply the bottom and top by x2 minus j2. So if I can jump here a little bit, we say that we simply multiply by the complex conjugate. Okay, the complex conjugate of the denominator. And how do we get the complex conjugate? Is that if we have z as that, then the complex conjugate denoted by z star, okay, or sometimes people say z bar, okay, is you just change the sign of the imaginary part. So if you can go back here, z1 divided by z2, you have, this is the numerator, and then we have the denominator. So we multiply both the numerator and denominator by the complex conjugate, which is got by just changing the sign of the imaginary part here. So this from a plus to a negative, and then that is it. And then we just do the usual procedure what we have been doing. Okay, so in here the idea is to get rid of these the imaginary parts in the denominator. So you usually end up with a situation where you have in the denominator you have a whole number, and then this is, okay, not as such a whole number, you have a real number, okay, and then also this is a real number. Okay, so an example here is given. If we have z1 and z2, then z1 divided by z2 is that, then you multiply by the complex conjugate of that, which is this. Okay, and then you can just follow step by step because the rest of here is just algebra. Okay, then you can answer the following the rest accordingly. Find the real and imaginary parts of the complex number z plus 1 over z for z is that. So it's just algebra. So you have z, oh sorry, it's not z plus 1, it is z plus 1 over z. So z plus 1 out of z. So we have z already given to us. Okay, oh, z is this one here. Okay, so z plus 1 over z, so this is our z which is given to us. Okay, so okay, you can just z is given to us, z, which is a quotient 2 plus j over 1 minus j, then you do what we have done, okay? Multiply both numerator and denominator by the complex conjugate, okay? And then this is what you get, and then 1 over z is the same as z inverse, okay? Then what we are simply going to do is, okay, someone could have said z inverse, someone could have said it is 1 minus j over 2 plus j, then you solve for that. However, since this has been already simplified to this here, then you can as well start from here, but z inverse is simply going to be 2 over 1 plus j3. Then again, multiply both numerator and denominator by the complex conjugate. You can as well do it from here. You can multiply both numerator and denominator by the complex conjugate. You should be able to get the same result, okay? So next we talk about the complex conjugate. Here are a few properties here. So in the angle diagram, since we are just changing the sign of the imaginary, i.e. the value which appears on the whole vertical axis, okay, that means that z star is simply the mirror image of z in the real or the x-axis, okay? So yeah, so and the following results can easily be deduced, okay? So you can simply deduce the following results. Okay, z plus z star, I think it's easier if you just have a few examples, but for now it's okay, we don't need to go into that. But you know that z, okay, if z is a plus that, then z star is a minus that, okay? Then if you add the 2, this is z plus z star is going to be 2a and then plus 0, but 2a is twice the real part of z, okay? So you have that, and then you have z minus z star is going to be 2 times 2j, okay, times okay, twice the imaginary part of z, okay, twice 2, okay, it is 2j times the imaginary part of z. Remember, the imaginary part of z is simply just the figure here, okay? We can do this here. So we subtract, and then z minus z star, this is that, and then this is minus j into b plus b. So it is minus j to b. So it is twice j. Oh, this is no, it's not, there's no negative here, it's this and then this minus that, that is going to be 2. This is b plus b, and then that is that, so it is 2j, but then b is the imaginary part of z. The imaginary part, yes, okay, the scalar simply. So others follow also. When you get z times z star or z bar, whatever it is, you get x squared plus y squared, i.e. you square the corresponding, it is the sum of the square of the real parts, and then z1 times z2, then you take what is it, then you take the complex conjugate. It is the same as saying the complex conjugate of z1 times the complex conjugate of z2, okay. Okay, so what do they say? That with the next to last result indicating that the product of a complex number and its complex conjugate is a real number, okay. Product of a complex number and its complex conjugate is a real number, okay. Okay, what next? So what are they saying here? Oh, they say that the zeros of an irreducible quadratic function which has real coefficients are complex conjugate of each other. So if this is irreducible here, and then we use the quadratic formula method here, then we can now say that these two zeros form a conjugate pair, because z1 is 3 plus 2j and z2 is 3 minus that. Okay, so these are complex conjugate, okay, complex pairs of each other. Then what else here? Okay, these are just other examples. Find all the roots of the quatic equation here. So what do they do? All the quatic equation here, you make use of the fact that you can write it as that plus what? 4x squared plus 16 equals to 0. Okay, then maybe you first factorize this one here, and then what do you have here? Let's say, oh, okay, how do they write it? Okay, maybe this, maybe it may work, maybe not, I don't know. Yeah, perhaps it could work, maybe. Let's see. Okay, let me not write something different here to really have it written here. So what do they do anyway here? This is that, so you have x plus 4 then squared minus 4x. Okay, they use the difference of two squares. You can use the difference of two squares, you reduce that, then again you have this is a difference of squares. Okay, no, do you use this is the difference of two squares, but then how do you come from this to that? You come from this to that by, okay, this is this plus 8x plus 16 minus 4x squared. Yeah, I know, I don't know, whatever way you can get to this. I think you can get to this by just trying to factorize this, okay, by maybe letting your x squared be something like a, this is going to be a, so you can just factorize this, but you know that a is x squared. Then you kind of reduce it until you come to this form here, and then your difference of two squares and so on, and then in the end you equate that to 0, and then we have the four roots, okay, which form two conjugate pairs. Okay, so they say that for the complex numbers z1 and z2 you want to verify the identity, which you can as well do so, just follow that and you know, and follow what is written here and do so. So what else? We talk about the modulus and the argument here. Okay, so maybe I can just go straight here. So if you have a complex number here, p, okay, we have a complex number z, and p is the position of this one here of z, then r here is called the modulus. Okay, the modulus of our complex number here is r. This is the distance here, but we know that to get that distance r, it is just the square root of this one here from our Pythagoras theorem, x squared plus this one here plus y squared. So we also have a relationship that since z is what, the square root of x squared plus y squared, we can square both terms, and then we have that z squared is x squared plus y squared, but we know that this one here is the same as the z times z star. Okay, yes, the relationship that they deduce here. So again, r is the modulus here, which is just the square root of x square root of x squared plus y squared, and then the argument of z is the angle theta. Okay, which angle theta we can just determine by saying from the relationship that the tangent of theta is equals to this vertical distance over x here, the horizontal distance. However, since you know that theta plus 2 pi will always represent the same angle, the same point. Then we have the principal argument. This is what they call the principal argument here. Is just the principal argument, the theta here, the argument is just restricted for those values which are between negative pi and pi. Okay, so that's why they say that if you really want to, so as not to make many mistakes, it is always good you just calculate. I mean, you can just start with a simple plot so that you know the angle which you are computing for. Its argument is simply that angle which is between negative pi and pi. Okay, so the rest here, excuse me, are just examples here. For instance, you have this one here, which is this one here, and then they ask for the modulus, which you can get the square root of x squared plus y squared. Where is that? Where is that? Where is that? Here. Okay, square root of that plus that, and then its argument, which is just tan inverse of 2, okay, over 3, okay, which will give us as in radians, okay, that is 0.588. Okay, so what else? Yes, then the rest is the same here. The modulus